This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 10 of Week 3, Heat Exchangers. The overall coefficient U that bundles both fluid films and the wall into one number. The log mean temperature difference method for sizing, and the effectiveness NTU method for when an outlet is unknown. Every heat exchanger problem starts from one equation, Q dot equals UAF delta TLM. A heat exchanger moves heat from a hot stream to a cold stream across a wall. No mixing. U is the overall coefficient, both films and the wall in one number. A is the surface area U references. F is the multipass and cross-flow correction, one for simple counter or parallel flow. Delta TLM is the log mean temperature difference. The rest of the topic is computing U and delta TLM, and, when an outlet is missing, sidestepping it with effectiveness NTU. The reference picture, a concentric tube counterflow exchanger. One fluid in the inner tube, the other in the annulus, moving in opposite directions, which keeps the temperature difference more uniform and extracts more heat than parallel flow for the same area. Hot enters at THI and leaves cooler at THO. Cold enters at TCI and leaves warmer at TCO. Hot in meets cold out at one end, hot out meets cold in at the other. Those four corner temperatures are exactly what the LMTD formula needs. The overall U is a chain of series resistances. The hot film, the tube wall, the cold film, plus fouling on each surface. The handbook builds it as 1 over UA, 1 over HIAI, and 1 over HOAO are the convection films. RFI over AI and RFO over AO, the fouling resistances. The natural log term conduction through the tube wall. Like the resistance networks in Topic 2, series resistances add, and the largest term dominates U, usually the weaker fluid film, an oil or gas side. For a thin clean tube, the wall and fouling terms drop out, leaving 1 over U, roughly 1 over HI plus 1 over HO. Before any LMTD work, the same heat rate ties the two streams together. Hot mass flow times specific heat times the hot temperature drop equals cold mass flow times specific heat times the cold temperature rise. Hot loses heat, cold gains the same. Define the capacity rate C as mass flow times specific heat, the heat carried per degree. CH for hot, CC for cold. This finds a missing outlet and feeds both methods. The stream with the smaller capacity rate changes temperature more. It limits the exchanger and becomes Cmin. The LMTD method. Because the gap between the streams varies along the length, the correct average is the log mean, not the arithmetic mean. For counterflow, delta TLM is the difference of the two end gaps over the natural log of their ratio, pairing hot out with cold in and hot in with cold out. For parallel flow, the structure is identical, but the gaps pair both inlets and both outlets. If the two end gaps are equal, the formula is indeterminate, and delta TLM equals that gap. For the same temperatures, counterflow gives a larger delta TLM, more heat per unit area than parallel flow. The classic error is mixing up the pairings. The effectiveness NTU method. When an outlet is unknown, you can't form delta TLM, so this recasts everything in dimensionless groups. Effectiveness, epsilon, is actual heat transfer over the thermodynamic maximum. Q dot max equals Cmin times the difference of the two inlet temperatures, the smaller capacity rate times the largest possible span. NTU equals UA over Cmin, and the capacity ratio CR is Cmin over Cmax. Each flow arrangement has a closed form relation among epsilon, NTU, and CR. Get epsilon, multiply by Q dot max for the heat rate, then back out the unknown outlet from the energy balance. No iteration. Q dot max uses Cmin because the limiting stream can at most exit at the other inlet temperature. The effectiveness relations the handbook prints for the concentric tube geometries. Parallel flow. Epsilon equals 1 minus the exponential of minus NTU times 1 plus CR over 1 plus CR. Counterflow with CR not 1. Epsilon is 1 minus the exponential of minus NTU times 1 minus CR over 1 minus CR times that same exponential. When CR equals 1, counterflow collapses to epsilon equals NTU over 1 plus NTU. And CR equals 0, a condenser or evaporator where one stream changes phase, gives epsilon equals 1 minus the exponential of minus NTU. That case is the workhorse for condensers and boilers. The phase-changing stream holds constant temperature, so only the other stream's capacity rate matters. These relations are also published as charts. The decision. Which method? Both solve the same equation. The choice is about which temperatures you have. All four known? Use LMTD. Compute delta TLM directly, then solve for whatever's missing, usually area or U. That's a sizing problem. An outlet unknown? Use effectiveness NTU. You can't form delta TLM without it. An LMTD would force iteration. Effectiveness gets the heat rate in one shot. That's a performance problem. Signatures, mass flows, specific heats, inlets, and UA ask for outlets or heat rate. Effectiveness NTU. All temperatures ask for area or U. Worked problem. Hot oil is cooled by water in a concentric tube counterflow exchanger. The oil flows at 2 kilograms per second, specific heat 2100, entering at 150 Celsius and leaving at 90. The cooling water flows at 1.5, specific heat 4180, entering at 25. The overall coefficient is 320, and F is 1 for simple counterflow. Find the cold water outlet, then the area required. The outlet is unknown, but the oil side is fully specified. The energy balance gives it. Then, all four temperatures are known, and LMTD sizes the area. Gather every quantity in the variable table before substituting. The hot oil side, mass flow, specific heat, inlet, and outlet, all given. The cold water side, mass flow, specific heat, and inlet given, with the outlet to solve from the energy balance. Then the overall coefficient, F equal to 1, and the area to solve from LMTD. Two unknowns, the water outlet and the area. Everything else is given. Step 1. The oil side is fully known, so start there. The heat rate is the hot mass flow times specific heat times the oil's temperature drop, about 252 kilowatts. That same heat rate heats the water, so the water balance gives the cold outlet, the inlet plus the heat rate over the water's capacity rate, about 65.2 Celsius. All four temperatures are now known, so LMTD applies. Step 2. The LMTD, then the area. For counterflow, the two end gaps pair opposite ends. Oil inlet minus water outlet, and oil outlet minus water inlet. Their log mean, the difference over the natural log of the ratio, is about 74.4 Kelvin. Then the area is the heat rate over U times F times delta TLM. Final answer, about 10.6 square meters. 4 checks. Units watts over watts per square meter Kelvin times Kelvin gives square meters. Energy balance. The water's heat gain matches the oil side. LMTD sanity, 74.4, sits between the two end gaps and just below their arithmetic mean, as the log mean must. Effectiveness crosscheck. C-min is the oil. Q.max is C-min times the inlet span, and epsilon is about 0.48, reasonable for a single pass. The oil is C-min because it shows the larger temperature change. 5 traps that quietly cost points. 1. Arithmetic mean instead of the log mean. The average overstates the driving difference and undersizes the area. 2. Wrong end gap pairing. Counterflow pairs hot in with cold out and hot out with cold in. Parallel flow pairs both inlets and both outlets. 3. Forgetting F for multipass or crossflow. F equals 1 only for simple single-pass flow, and shell and tube or crossflow need an F below 1 from a chart. 4. Wrong C-min. It's the smaller capacity rate, mass flow times specific heat, not the smaller mass flow, and Q.max uses the two inlet temperatures. 5. Picking the slow method. All 4 temps known means LMTD in one line. An unknown outlet means effectiveness NTU with no iteration. Bookmark section 5.5, heat exchangers, 3 printed pages. The rate equation Q dot equals UAF delta TLM. The overall U, the series chain of both films, the wall and fouling. The LMTD forms, log mean of the two end gaps, counterpairing opposite ends, parallel same ends. Effectiveness, epsilon equals actual over maximum. Q dot max set by C-min and the two inlets. NTU, UA over C-min. And the effectiveness NTU relations, closed forms for parallel, counterflow, CR equals 1 and CR equals 0. Tab the relations especially. They're tedious to reconstruct under time pressure. Up next, Topic 11, Radiation Heat Transfer. Topics 1 through 10 covered conduction and convection, heat through matter. Topic 11 turns to the third mode, radiation, which needs no medium. We'll meet the Stefan-Boltzmann law, emissivity and the gray body model, view factors, and radiation exchange in enclosures. The key shift: radiation scales with the fourth power of absolute temperature, so Kelvin is mandatory and the math turns nonlinear. See you in Topic 11.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.